Hello and welcome. In our last segment, we learned to show our linear inequality solutions on a graph. For consistency and ease with graphing, we put statements into standard slope-intercept form, like this example, y is greater than 2x minus 3. By setting it to an equation, we can find a table of values, intercepts, or use the y-intercept and its slope to generate a line that will form a boundary of our solution. If the points on the line are part of the solution, we use a solid line. If they're not, a dashed line is used. Our example doesn't include equal to. Another advantage of the standard form is that it allows us to use the direction of the inequality sign to quickly determine if our solution lies above or below the line, without having to test points on each side. Greater than means to include the values above, and less than means to shade below. Let's extend this now to learning about systems of inequalities. Recall for previous work that the term system is used when we have more than one thing working together. With systems of equations, we have the option to solve them algebraically, because the equal sign allows us to substitute out one of the variables. Or you can use elimination to find your answer. Here's an example of substitution. Isolate the x for one of the equations and substitute that value in the other equation to leave only the y. To simplify to solve for y, we get y is equal to 2. Now substitute 2 in for the y in one of the equations, and we get x is equal to 2. So our solution is the point 2, 2. You also likely learned to solve by graphing. Because our two relationships have the same variables, we can show them on the same plane. We see that our solution is once again the point 2, 2. This is, of course, the intersection of the two lines, the only point that is common to both equations. The only method to solve a system of linear inequalities is graphically. Perhaps that is welcome news. Let's start with this linear inequality in standard form and show its solution. The sign directs us to use a dashed boundary line and a shade above. A second linear inequality with its graph. Notice the solid green boundary line as it includes equal to, and the less than sign means the solution lies below the line. Now we can show them together and evaluate the possible solutions. By showing the graphs in this way, it's easy to see common points or the intersection of the two graphs. Check a point from this area that will prove it's true for both restrictions, like the point 0, 0. In the first inequality, we get 0 is greater than -1, which of course is true. And in the second, we get 0 is less than or equal to 1, which is also true. We can keep adding statements like this third restriction, which effectively limits our solution even more, to just the small triangle near the center. Although it's most common to find the intersection of our inequalities, you may see that our solution could be the union of the statements. In this case, we would shade all values that satisfy either inequality, as union means or. Ultimately, we want to see where a system of inequalities might be utilized. Here's a pretty simple scenario to consider. Now, you've been given the responsibility of ordering pizzas for a party. The restrictions you've been given are that you must get at least 8 pizzas, either medium or large, and you can't spend more than $100. The pizzas are $10 for a medium and $14 for a large. You've done the math and you know you get more pizza with a large, but you also have many dietary interests and needs, so you must decide how many of each to maximize value and variety. We can set our conditions as follows. m plus l is greater than or equal to 8, which forms this inequality graph. And 10m plus 14l is less than or equal to 100, showing the restriction on spending. We have placed L on the vertical axis and M on the horizontal, and need only focus on the first quadrant. By graphing the two restrictions, we can see their intersection here. Perhaps the most obvious point is 3, 5. Maximum value for sure with the greatest number of large pizzas. Or 10, 0 for the greatest variety with 10 mediums. Any discrete value in the shaded area would work. Perhaps your decision is somewhere in between, like 5, 3, leaving a bit left over for a tip. When we combine inequalities with the same two variables, we show their solution on a graphing plane. These form a system that we can evaluate by viewing the results of the graph. In fact, a graph is the only way to present this information. As we've done in the past, we can consider both the intersection of our points or the union of them. We may also need to specify whether our data points are discrete, like the number of pizzas, or continuous. We will continue next with solving quadratic inequalities.